example number 3 for me. Given the mass of hydrogen-2, the mass of helium-3, and the mass of a neutron, you wanted to find the energy released. Now, to find the energy released, we have to know where the energy comes from. Where does the energy in a nuclear reaction come from? 2 words. MD. Mass defect. Good. The energy comes from the mass defect. And the mass defect in the context of a single nucleus would be the difference in mass between the nucleons, or the protons and neutrons, and the nucleus. The nucleus always weighs a little bit less than what makes up the nucleus, the nucleons. But in the context of a reaction like we have here, the mass defect is the difference in mass between the daughter nuclei and the parent nuclei. In other words, the products and the reactants. The products or the daughter will always weigh a little bit less than the parent or the reactant. Let's figure out what the mass defect is, and then let's figure out what the energy released is using Einstein's energy mass equivalence equation. On the left-hand side here, on the left-hand side, we add up 3.36 plus another 3.36, giving us the total mass of the reactants or the parent nuclei, gives us 6.72710068 times 10 to the minus 27 kilograms. On the right-hand side, we add up the mass of a helium nucleus and a neutron. When we add up the helium nucleus and the neutron, we end up getting 6.614 times 10 to the minus 27 kilograms. What do you notice about those 2 masses? They're almost the same, but the final mass, the mass of the daughter nuclei or the mass of the product, is a little bit less than the mass of the reactants, which is exactly what should happen, right? When we want to calculate the mass defect, we're going to subtract those 2. When we do that subtraction, we end up getting 4.603998 times 10 to the minus 29 kilograms. And now all we have to do is say E is equal to mc squared to find the energy released. The mass defect times the speed of light squared. And when we do that, we should get 4.14 times 10 to the negative 12 joules. Now, the answer is expressed in joules here because we use standard units throughout. We're going to get standard units for final answer. But on a test, it could absolutely, easily ask you to express this in electron volts. And if it did, you guys know the conversion, right? 1 eV is 1.6 times 10 to the minus 19 joules. We would say xeV is equal to 4.14 times 10 to the minus 12 joules. I won't bother solving for x there. Okay, but if you had to convert this to electron volts, that's exactly what you do. And if you had to convert it to, say, mega electron volts, then you just divide it by 10 to the 6, or divide it by a million. Okay, let's plug forward with what we were doing yesterday. We yesterday learned about 2 models of the atom. Can't get any better than that, right? It's a Thursday afternoon, and you guys are learning about not only the planetary model of the atom, but you get to learn about the Bohr model of the atom too. It doesn't get any better than that. The planetary model of the atom, which was derived from the gold foil experiment or the alpha scattering experiment, call it whatever you want, basically looks like this. You've got a small, dense, positive nucleus in the middle, surrounded by mostly empty space, but there are these little electrons that are orbiting around the nucleus in circles. That's a pretty good model of the atom. It's pretty good because it looks remarkably like the model of the atom that we currently accept to be correct. But Bohr kind of extended it a bit, kind of went further with it. He said that, yeah, there are electrons orbiting around a small, dense, positive nucleus, and most of the atom is empty space, but those electrons that orbit around have to orbit around on specific levels, electron levels. I used the saddle dome analogy yesterday when we were talking about electron transitions. Today I'm going to use the saddle dome analogy for something else. Okay, we're talking about electron levels. There's 3 levels in the saddle dome, and each level is characterized by a specific energy in the atom. It is in the saddle dome as well. If you go to a hockey game, you know that first level tends to be kind of reserved. You know, people coming from work, sometimes dressed in suits. Okay, they can afford the expensive seats. They're sitting there texting on their phones or checking their work email, and they're kind of reserved, right? They clap like this when somebody scores a goal for Calgary. But then the second level Okay, tickets are like half the price that they are on the first level. Okay, people are a little bit more excited. The second level is characterized by a different energy level. When Calgary scores a goal, people get up and cheer. Okay, people get up and clap and cheer. Okay, it's characterized by a specific energy level, a different level of energy than the people on the first level are characterized by. If you go up to the third level, if you've ever sat in the sport check zone, you know it's characterized by a completely different energy level up there. Okay, the people up there sometimes, I don't want to make generalizations, but sometimes, you're spending $40 up in the sport check zone. Sometimes people say, I could spend $40 on a ticket and sit up in the sport check zone, or I could spend $130 on a ticket and sit down in the second level. Okay, the extra $90 I'll save will buy me a lot of beer. So that third level tends to be characterized by a lot more energy than the first level or the second level, right? Those are the people that when Calgary scores a goal are getting up and high-fiving each other and falling over the seat in front of them and so on. Each level is characterized by a specific amount of energy. Okay, just like in the atom, each electron level is characterized by a unique specific amount of energy. Now, electrons, as they orbit around the nucleus, according to Maxwell, think back to your EMR unit, according to Maxwell, they should emit EMR. Why? Well, look at the keys up here circling around my head right now. As they orbit around the nucleus, they're accelerating. What do we call that acceleration? What type of acceleration is it? Centripetal acceleration, and it's always directed which way? To middle, towards the center of the circle. Maxwell didn't distinguish between types of acceleration. Acceleration of charged particles generates EMR. But guess what? In the atom, it doesn't. As the electrons orbit around the nucleus and experience centripetal acceleration, they should emit EMR according to Maxwell's theory, but they don't. It's as if these electrons aren't accelerating. It's as if these electrons aren't even moving. It's as if they're stationary. We call it a stationary state, where these electrons that should emit EMR don't emit EMR. But it is possible for electrons in the atom to emit EMR, just not as they orbit around the nucleus. What do they got to do to emit EMR? They got to change levels. They got to make a transition. That's when they emit the EMR, during the change in level, as opposed to as they orbit on a particular level. If they fall to a lower level, fall from the third level to the first level, or from the fifth to the third, or whatever, they emit energy. And that energy will always be in the form of EMR. They'll give off a photon, a visible light photon, an infrared photon, an ultraviolet photon, occasionally maybe an X-ray, if it's a really, really big high energy transition. But electrons can also jump to a higher level. The only way they could fall to a lower level is if they end up being on a higher level to begin with, right? So as they jump to a higher level, they're going to absorb energy. That's when you're going to the third deck of the Saturdome, and you want to make sure that you have pasta the night before, because it seems like it's 6 miles up in the sky when you're going to that third deck of the Saturdome. You need your energy, right? You need to absorb energy to go to that higher level. Usually that energy that the electrons will absorb is in the form of EMR, but not necessarily. It could be any energy. It could be electrical energy that the electrons absorb. It could even be kinetic energy from another electron that struck it, that gives it its energy and causes it to jump to a higher level. When it absorbs, it's usually EMR. When it emits, it's always EMR in the form of infrared, visible light, or ultraviolet. Now, I want you to flip over the page that you got yesterday that has 2 diagrams on it. The first diagram is going to look like this. This is going to describe for us in a little bit more detail what's happening with these electron transitions, that third aspect of the Bohr model of the atom. What I'd like you to do right now is draw a line between the first diagram and the second diagram. That first diagram is going to represent a reference diagram for us. It doesn't really have anything to do with the Bohr model of the atom per se. We're just going to use it to reference the last 2 diagrams, which do have something to do with the Bohr model of the atom and electron transitions. We're going to number this one diagram number 1, diagram number 2, and diagram number 3. Let's describe our reference diagram first, or our non-Bohr diagram first. In this one, you can see that we have a light bulb, an old style incandescent light bulb, or some other heated solid, or heated liquid, or heated gas under high pressure. When you have one of these substances, a heated solid, a heated liquid, or a heated gas under high pressure, it will produce electromagnetic radiation. In fact, it'll produce what we call a continuous spectrum. That's all the colors of the rainbow. And not like distinct red and distinct orange, but red transitioning into orange. It's a rainbow, right? You see the continuous spectrum there, but not when you look at the light bulb or the glowing solid. When you look at the glowing solid, it appears to be white light. So in order to see the rainbow or the spectrum that's produced, you actually have to put something in between your screen and your producer. And that would be either a diffraction grating or a prism, not both. The prism and diffraction grating split it up so that it looks more or less the same, the pattern that is, except that the prism would be Roy G. Biv, the diffraction grating would be Viv G. Orr, right? The opposite to that, right? But it's the same effect, essentially, just backwards, that's all. Continuous spectrum, okay, white light, separate into its colors, polychromatic light, separate into its colors, produces this continuous spectrum, this rainbow. It's what you see when you look up in the sky when it's raining. Okay, let's move to the second diagram, which does have more to do directly with the Bohr model of the atom. In the second diagram, you notice our source of EMR here is not a hot solid or a hot liquid or a hot gas under high pressure. Rather, it's a hot gas under low pressure. That produces EMR as well, but it doesn't produce all types of EMR. It's not a continuous spectrum like we have in the top diagram, diagram number 1. Rather, it produces only specific colors of light. Each of those colors would correspond to a specific transition that was taking place. So we might get a transition taking place within this hot gas from level 5 to level 3. That would emit a photon, a certain color photon. We might get another transition taking place from level 4 to level 1. That would produce a different photon or a different frequency, a different color. What you see on this diagram, this emission spectrum, or sometimes we call it a line emission spectrum, are those colors that correspond to the specific transitions that have taken place. It is not a continuous spectrum because you don't get all colors. All you're getting is a red and an orangish yellowish, and then a yellowish green, and a green, and a blue, and an indigo, and a violet, corresponding to unique, specific transitions that have taken place. Line emission, because electrons have gone from high level to low level, producing lines, specific photons. Okay, now let's fast forward to the last diagram, the third one, where we have pretty much the same thing as the first diagram. In fact, if we scratch out that cold gas, we have exactly the same thing as the first diagram. Don't scratch it out on your diagram yet, though. Look, we've got our hot solid or liquid under gas under high pressure, whatever it is, it's producing this EMR here. It's producing white light or polychromatic light. And when we put that polychromatic light through a prism or diffraction grating, it produces our spectrum. What kind of spectrum does it produce? Continuous spectrum. It's not the Bohr model of the atom here. We're not talking about electron transitions. We're just talking about our reference diagram. But watch what happens when I introduce the cold gas. We get a slightly different absorption spectrum in diagram 3 once I introduce the cold gas than we got from the first diagram. What's different about it? Yeah, there's no black lines in the continuous spectrum. There's black lines in this absorption spectrum. What do you think those black lines correspond to? Good. Well, specifically the transitions that take place within the cold gas. You just noticed, Caitlin just noticed that they happen to be the same transitions that took place in the hot gas, and we'll revisit that in just a second, okay? But the bottom line is you have a continuous spectrum produced by this hot, solid, liquid, or gas under high pressure, minus certain colors that seem to have been taken away, right? There's all this light minus colors that have been taken away. What were they taken away by? The cold gas. The cold gas absorbed photons, causing electrons to jump to higher levels. Remember we said a few minutes ago, electrons can fall and they give off EMR. Electrons can jump and they absorb energy, usually in the form of EMR. These black lines correspond to the missing photons, the photons that were taken away by the cold gas. Now, Caitlin also noticed that those photons, or those lines, are in the exact same positions and therefore the exact same frequency and wavelength as the lines produced in the emission spectrum. What do you know about this hot gas and this cold gas based on what Caitlin just noticed? Right? It's the same gas. Every element or compound produces a unique spectrum. So everyone is going to be different. I don't know what this hot gas is or this cold gas is, but I do know that because the spectrum for this hot gas is unique, and I got the same one for this cold gas, just in reverse because it's an absorption spectrum, I know it's the same gas. I had a professor in university, his whole academic life besides teaching was photographing atomic spectra. And I remember I never did this stuff in high school. So when I went to university and saw that he did this, I remember thinking like, why? Like you spent 40 years photographing atomic spectra, different transitions of electrons that are taking place in atoms. Without knowing anything about it, it seemed like it was a very, what's the word I'm looking for here? Trivial, tedious, almost seemed like a waste of time. But he explained to me one day why he was doing this. And it makes perfect sense to me now that I've actually learned about this stuff, right? And hopefully it will to you guys today. He would photograph them and then publish them in journals, in professional journals, these photographs. And then people, physicists, astronomers, would read these professional journals and they'd say, hey, well, that's a neat spectrum, whatever. But it goes beyond just looking at a spectrum and saying, hey, that's a neat spectrum. Let's say Kobe is an astronomer and he's looking at the night sky and he sees a star and it's not on a map anywhere. Nobody's ever noticed the star before. Nobody's ever discovered it before. So he's just discovered a star that nobody's ever seen before. And that happens. Still, that happens. Sometimes it even happens by young people. Like I've heard stories of kids, 10, 11 years old, discovering a star that nobody's ever discovered before. Kobe wants to find out what that star is made out of. So he looks through a spectrometer, which is basically a prism or diffraction grating, and he looks at the spectrum being produced by this star that is made up of a hot gas. And he compares that spectrum against the known spectra or the spectra that were photographed by my professor or by somebody else, because he wasn't the only person doing this stuff, right? And compares it, knowing that the spectrum of hydrogen and helium and whatever is unique. He's able to compare that spectrum and determine the composition of that star simply by looking at the spectrum that's produced from the light, or from the transitions of electrons, I should say. Make sense? Take a look at the second diagram on your page. It's this one up here. This gives us 3 reference spectra, not in color. This was a question that appeared on an exam almost 20 years ago, back before they used color. They still don't use very much color. But if you get a diagram like this now, it would probably appear in color. You can see that you have multiple lines in hydrogen and in helium and in sodium as well, each corresponding to a different transition of an electron from a high level to a low level in that atom. These are photographed by my professor or by somebody else that does the same kind of work. But then Kobe looks at the star and sees an unknown gas mixture spectrum. Doesn't know what's in it, so he wants to determine what's in it. He opens up the little atlas of atomic spectra, pictures, and he looks at the pictures and he says, oh, wait a second. Every single line of hydrogen, every single line of the hydrogen spectrum is in this unknown gas mixture. Therefore, this star must be made at least partially of hydrogen. He's just determined the partial composition of this star. Is there anything else in the unknown gas mixture? We know there's something else, right? Because we've accounted for this line and this line and this line and this line. That's from the hydrogen gas spectrum. Let's just check helium for a second, okay? I know that Nick said it's sodium, but let's just double check helium here. Helium has this one, this one, this one, this one, this one. This one's there, right there, corresponds to one of the ones from hydrogen. But none of the rest of them are there. So is helium there? No. We know there's hydrogen, but we know there's not helium. Let's keep going. Sodium. There's only 2 lines in the visible spectrum for sodium. Are they in the unknown gas mixture? Yep. So what does that tell us about the composition of the unknown gas mixture? It's hydrogen and sodium. Make sense?